So tonight we're going to talk about DeepHyper. I just have one sentence here that I'll talk about a little bit. It's a software package that uses scalable neural architecture and hyperparameter search to automate the design and development of deep neural network models for scientific and engineering applications. That is like a 30,000-foot view of what we're going to talk about tonight. But without further ado, Prasanna, I think I'll hand it over to you and let you sort of take the conversation from here. Thanks so much for being here.
Thanks, Justin. Thanks again for the opportunity and for the introduction. Good evening, everyone. My name is Prasanna Balaprakash. I'm a computer scientist at the Mathematics and Computer Science Division, and I also have a joint appointment at the Leadership Computing Facility. So the Math and Computer Science Division is a division where we do research, and the Leadership Computing Facility is the one that runs the supercomputers for Department of Energy. I'm from Argonne National Lab, and today I'm going to talk about democratizing deep learning development with DeepHyper. So before entering into the topic, I want to give a high-level overview on the national labs, and in particular Argonne. So national labs are sort of set of it's composed of a number of research labs, and it's sort of science with respect to national interest. And there are a lot of research that goes on here, sort of starting from how the universe works to solving hard problems in materials, all the way to sort of contributing to the humanity with respect to drug discovery and climate change and related research. So U.S. Department of Energy is sort of U.S. Department of Science, and we have the DOE National Lab System is one of the largest scientific research system in the world. It is the National Lab System sort of were formed and grown out of the nuclear research. In particular, the goal was to develop atomic bombs during World War II, and there were foundational and applied research that were happening, and that sort of formed the basis for these national labs. But these labs sort of grew out of that sort of focused mission, and now it is sort of focused on really big science, multidisciplinary teams solving really large-scale, complex R&D challenges which are otherwise impossible. So think of a really grand challenge problem, and that problem requires hundreds of people working with some sort of single mission and trying to solve problem in a collaborative environment. So that's where the national labs come in. And national labs conduct research from basic all the way up to very applied, and all in the context of Department of all in the context of energy and energy mission needs. And you can see some of the budgets from the DOE and compare that with the DoD and NSF and NASA. So it's a heavy investment in the infrastructure, in the national research infrastructure, and the people and the type of research that we do. There are many important discoveries and innovations that were from DOE national labs. For example, much of advances in supercomputing thanks to the national labs. If you have followed recent news, we broke the exascale barrier. So which means that there is a first exascale system in the US at Oak Ridge National Lab, and that is primarily due to research happening at the DOE labs. And supercomputers are sort of it's not it's a sort of a time machine if you think of it. Like whatever you have in your phone is basically a supercomputer 20 years ago, right? And whatever we have as a supercomputer now, which that will be available on your desktop, probably on your laptop, probably 10 years from now, right? So the supercomputers are not a one-off system that were designed to solve a specific problem. It actually pushes the computing barrier and the computing envelope, so that the amount of computing power that is available to solve interesting problems become available and become cheaper as we improve the technology. It's I'm from that area, so that's why I spoke a little bit more about the supercomputing. But there are several other research innovations, starting from optical digital recording, ceramics, and biological process of photosynthesis, all the way up to materials manufacturing, medicine, transportation, and safety, security, and nuclear stockpiles. So those are all a wide range of research that are happening across national labs. And in fact, there were discovered 16 elements and quarks, thanks to research happening at the national labs. There are 17 DOE national labs, and you can see the maps. You can see the location in the maps, and some of them are open science. For example, Argonne National Lab, Fermi, Ames. We do open research, open science. Whereas Lawrence Livermore, Sandia, and Los Alamos, they primarily do sort of a weapon science. And some of the labs are single mission, and some of the labs are sort of a multidisciplinary. For example, Fermi is a single mission lab, whereas Argonne is a multidisciplinary, multiple research, multiple areas of research happen in the lab. And it is distributed geographically across the whole country. So irrespective of the state you are in, you will be able to find a national lab somewhere near, and please do check out what is happening in those labs. And as I said, the single program labs are Princeton Plasma Physics Lab, which is focused on fusion energy and building fusion energy reactors, whereas these labs, Brookhaven, Berkeley, SLAC, Argonne, Oak Ridge, these are multi-purpose labs where we conduct research across various domains and various applications. So here is a short video on Argonne, focusing primarily on what Argonne is
Argonne National Laboratory plays a vital role in our everyday lives, forging tools and technology to help improve and shape the world around us. Whether we're designing fuel-efficient engines that produce fewer emissions and help fight climate change, or identifying weaknesses in deadly viruses that lead to the design of treatments and vaccines, our research addresses some of the world's most important science and technology questions and pursues solutions to everyday problems. Born of the Manhattan Project, Argonne was chartered as a national laboratory in 1946, dedicated to pioneering the development of nuclear technology for peaceful uses. The laboratory's legacy of developing new energy sources has expanded to cover an awe-inspiring range of research areas, from computational sciences that merge innovative data and analysis tools to solve complex problems, to X-ray sciences that illuminate how materials are structured and how they work, both here on Earth and beyond, to the materials sciences that develop safer, more reliable materials for batteries, engine parts, and more. But solving society's grand challenges requires leadership, knowledge, a diverse workforce, and powerful tools. Argonne is home to 5 Department of Energy user facilities that support the research of nearly 8,000 scientists every year, enabling science at tremendous scale. Each facility provides unique tools and world-class expertise to support industry, academia, and other research institutions globally. With future upgrades of 2 of our facilities, the Argonne Leadership Computing Facility and the Advanced Photon Source, we are poised to transform scientific discovery and innovation, opening doors to exciting new technologies and greater insight into ourselves, our planet, and the cosmos. 75 years after its charter, Argonne continues to pursue its mission to provide the nation with clean, efficient energy sources and drive research that enables energy independence and protects our critical infrastructure in the face of natural disasters. And as society's engagement with technology evolves, Argonne continues to accelerate science in partnership with businesses and universities to revolutionize scientific discovery through artificial intelligence, further our understanding of energy and matter in the universe, harness the quantum world, and advance manufacturing to strengthen our economy and national security. For 75 years, Argonne has met the scientific and technical challenges of the day, and today, more than ever, we want to assure our actions benefit everyone equally. We continue our efforts in STEM outreach to underserved communities and to increase diversity and inclusivity at our laboratory and beyond. We work to assure that the results of clean energy research benefit people of all backgrounds and that all communities are resilient against the effects of climate change. Challenges may change in the future, but Argonne's commitment to excellence in discovery and innovation and dedication to a just society will not. This is Argonne, transforming science, improving your life.
Okay, so that's a 10,000-foot view of what we do here at Argonne. And the next video is again on Argonne, but in particular the exascale computing efforts and how exascale is actually transforming various types of science we do here at Argonne. Here is again a short video that describes our exascale computing efforts.
Argonne's mission is to advance fundamental science research. What the Intel and Cray partnership is going to make possible is pushing the envelope from neuroscience to urban science to material science to cosmology to cancer research to microbiome research.
The Aurora system is pushing forward the boundaries in simulation-based computational science, data-intensive computing, deep learning, and machine learning. This will have a broad impact on the full HPC ecosystem.
What excites me the most about exascale is the fact that we have in one environment the ability to mix simulation and artificial intelligence. And we have this integration of big data, of data-driven science, streaming data, and simulation. That's where science is going to happen. That is where breakthroughs will happen.
Exascale computing is going to have an amazing impact on our work. The machine will allow us to look at alternative types of algorithm, do things which might have taken many months and many days to look beyond the standard model and hopefully make some discoveries.
My work is in computational fluid dynamics, using computers to model and predict fluid flow around aerospace vehicles. By having a better predictive capacity, engineers will design more fuel-efficient planes.
The Aurora system will be based on future generation of the Intel Xeon Scalable processor, technologies based on the future XE architecture, the next generation of our Intel Optane DC persistent memory. This will all be supported by one API. This is our next step in really solving those grand challenges that we face.
Exascale is going to change pretty much everything.
Okay, so now I showed various types of applications and various types of computing effort here, happening here at Argonne, and I have pretty much convinced you that the type of applications that we deal with is quite, it's quite diverse, right? So various types of applications, and each application has their own sort of characteristics. It's not one size fits all. And if you have seen a common thread the ability to predict physical system, ability to simulate physical system and predict what will happen with those physical systems, our complex systems, our engineering systems, is more or less the sort of the central piece across various applications. And that's why artificial intelligence and machine learning is so important to broad range of applications, right? So far we were looking at simulations and use simulations to predict what will happen, right? Now we can use simulations and machine learning to predict what will happen in those systems. And that's why there's a lot of interest in incorporating machine learning, not as a sort of a separate entity, as a part of each and every workflow that we deal with, starting from subatomic particles all the way up to cosmology. All these applications generate a lot of data. And even if they don't generate a lot of data, we have to have a mechanism to predict the behavior of the system or the physical phenomena and so on and so forth. So, just at Argonne alone, we have more than 100 plus AI ML applications, and each of these application is sort of unique in its own way. So for example, a model, let's say a predictive model that is developed for molecular dynamics, you can take that and put it into weather, right? Or you take something from transportation, trying to predict what will happen with the traffic, and apply that to cosmology, right? So these are all different applications, different modalities. The data is different, the characteristics is different, and we have to develop various types of models for these data sets, right? So that is one of the biggest challenge that we face in various types of applications. And if you take a step back and say, okay, even take a simple neural network. So I'm going to talk about neural network throughout the whole presentation, but you can replace neural network with any type of machine learning model like XGBoost or random forest or Gaussian process regression, anything, more or less all these things that I say apply. But for the sake of discussion, let's focus on neural networks because of its ability to process large amount of data and to provide a good prediction accuracy for various types of applications. So if you look at this simple neural network, you can go and do this in a playground.tensorflow.org, where you don't have to write any code. You can just go and configure neural networks like this pictorially and add neurons in the hidden layers. And you can choose whatever the data set that you want, and then set some parameters such as learning rate, activation, regularization, and then run the training. So this is no code training, a no code deep neural network pictorial way to design a neural network and see how your training accuracy, in this case training loss and the test loss looks like. So it's a simple neural network on a simple data set, spiral data set, classification data set, and you can see a training loss and the test loss going more or less hovering around 0.3, right? For the same network, keeping all the parameters same, all the hyperparameters same, you just go and add one more neuron here and here, right? So all that is different from the previous neural network to this neural network is just adding 2 units in the 2 hidden layers. And now you can see the training loss has moved from 0.3 to 0.015, right? And similarly, the test loss moved from 0.3 to 0.06. That's a huge improvement. And we are talking about simple neural network with 4 layers, right? And a simple data set. The kind of outputs or the kind of accuracy that we get is different if we change these type of neural network parameters, right? If this is the case, think about the complexity that we have to face with scientific applications. For example, this is a neural network that we have to design for molecular property prediction. So this is a graph neural network. And again, for a simple graph neural network, we have to decide what type of message passing neural network layer that we have to use and how to connect them. And within that message passing neural network, there are various types of channels, attentions, and heads that we need to configure. And we have to then use skip connections to make the neural network behave well. So even for the simple graph neural network, we are talking about 10 to the power of 10 possible designs. And often how the domain scientists or even AI expert, ML expert configure this type of neural network is to do trial and error. Okay, so I start with some neural network that for this particular problem that was published or available on GitHub, I take that and then say, okay, let me start this and then start tinkering around. Like, so it's a very manually, it's a very manual process, trial and error and a time-consuming process. It's also jokingly called as a graduate student descent, which means that you keep on improving by changing certain parameters and the architecture variables of the graph neural network. So that's a sort of a typical workflow. So none of these sort of work like, okay, take this model, download that from the GitHub graph neural network, apply it to a scientific data set, which is completely different from what it was designed actually. Then you see what the accuracy is. It's not the one that you will get as you would expect, right? So this is a big problem, and this is a problem that sort of hinders the scientific discovery as a whole. So if you think about what are all the degrees of freedom in designing neural network, you can think of two different set of hyperparameters. One is algorithm hyperparameters. The other one is architecture hyperparameters. The algorithm hyperparameters are the one in which you say, okay, I fix the neural network architecture. So let's say I fix the convolution neural network or a LSTM type network, but then for the given data set, I need to find what is the right type of optimizer, what is the right learning rate, mini batch size, learning rate scheduler if it has parameters, or adaptive batch size parameters, and so on and so forth. So for a fixed architecture, how can I adapt, or how can I find the right set of hyperparameters? Okay. On the other hand, you also have architecture hyperparameters, where you look at how to change the architectures itself, right? And in terms of let's say if you're looking at a data set where you need different types of recurrent neural network, or you want a RNN or a long short-term memory type network, or GRU, or so on and so forth, right? So those can become architecture hyperparameters, or the type of layer, right? So you can use fully convoluted, fully connected layer, or a convolution layer, or recursive layers, and so on and so forth. You all can also put different types of skip connections, because skip connections change the architecture as a whole. So essentially, whatever the hyperparameters that changes the neural network architecture, you can put this in the class of architecture hyperparameters, right? So if you have these two classes of hyperparameters, then we can think about formulating an optimization problem to come up with a principled way to design neural networks. And this optimization problem is formulated as a bi-level optimization problem, where the low level problem, it has two levels, upper level and the lower level. The lower level problem is the one that we often deal with, right? So we take the data, right? We take the training data. So the lower level problem works on the training data. And what we often have is we always have a fixed architecture variable and fixed hyperparameter variables, right? So fixed hyperparameter values. And then we go and train a network so that its training loss is lower, right? Of course, you use some other data, validation data, to stop the training, but essentially the lower level problem is all about training the model. The bi-level optimization problem that we are talking about is one level upper, where you say, okay, so the lower level problem uses algorithm hyperparameter and architecture hyperparameter fixed. At the upper level, what we want to do is parameterize that space. So capital HA is architecture hyperparameter space, the full space, and capital HM is algorithm hyperparameter space. Okay, so full space. And a particular sample from that space is small HA and small HM, right? So for a particular sample from this space, we go and train the lower level problem. So essentially, which means that if you have to minimize the upper level problem, the upper level problem works on the validation data. So let's say if you are maximizing accuracy, right? So let's say if you are maximizing accuracy, then the upper level problem is it's a maximization problem where we want to maximize the validation accuracy, okay, subject to minimization of the training loss, right? So this is the usual problem, and this is the one level upper where we say we will change the hyperparameters, both algorithm and architecture, and maximize the validation accuracy. So okay, so this problem is a very hard problem, and solving this problem requires new algorithms and new scalable infrastructure. So DeepHyper project is looking at this problem and developing software to address this bi-level optimization problem. DeepHyper software consists of two components: a search component, which has hyperparameter search, which basically identify the right hyperparameters for a given neural architecture. And neural architecture search is basically search over different neural architectures to find the best architecture on a given data set. And joint neural and hyperparameter search is a sort of combination of both. And the component that I'm not going to focus on today is a workflow component, which is very, very critical, which basically sort of a backend for doing the search, where it takes different architectures, different different neural networks, and train them in parallel and give the results back to the search. And using that, the search sort of iteratively improves the model performance. So we'll be touching that a little bit, but the focus will be primarily on the search component, how to solve that bi-level optimization problem. First, we will focus on the hyperparameter search. So to search, for example, given a network, and if you have to go and optimize its hyperparameters, then this problem can be solved effectively using Bayesian optimization. So a quick primer on Bayesian optimization: it works on the key principle where you have a probabilistic model. So as opposed to the usual model where you predict only, if you want to do a prediction, you get one value, right? So instead of that, the probabilistic model not only gives you the prediction, but also sort of a confidence interval around that prediction. So it's essentially an uncertainty associated with the prediction. So we call that as a posterior distribution. So the idea is simple, right? So you can see that you have the input and output, right? So think of this as an input-output pair for a supervised learning, and these black points are the points that are available to the Bayesian model. So in our case, the black points are the hyperparameter configurations and its corresponding accuracy values, right? So if we take these two as a pair and fit a probabilistic model, then what happens is you have a model like this. So this is an example probabilistic model, Gaussian process regression, where you have multiple functions that pass through the given point. And farther away from the point that you have, your uncertainty will be higher, right? Because you don't know about those regions. On the other hand, the closer you are to those black points, your uncertainty will be very, very small because the model is confident about its prediction. And one can leverage this uncertainty from the model to decide where to sample next. And that's the key idea behind Bayesian optimization. So typical Bayesian optimization works as follows. You are given the observations xi, yi. So xi here is hyperparameter configuration, and yi is the corresponding validation accuracy, right? So the Bayesian optimization incrementally build a probabilistic model, right? So you start with some randomly chosen configurations, fit a Bayesian model, right? And you select where to sample next, because you cannot just you can randomly sample, of course. That is called random search, and that is being used widely. Random search and grid search has been used widely for the hyperparameter search. But Bayesian optimization is a lot more informative, a lot more focused search, where you don't have to spend a lot of evaluations, because each evaluation is expensive, right? So you don't have to spend a lot of evaluations to identify the best performing configuration. So you start with this, and then using that uncertainty, and that uncertainty goes into something called acquisition function, right? And that acquisition function decides put score on the whole input space, which is then used to find where to sample next. And the acquisition function's main role is to balance exploration and exploitation. Exploration means it will go and sample in the regions where the model says, okay, I have high uncertainty, which means that I haven't explored hyperparameter configurations in this region. So go on and give me samples so that I can improve my predictive capability. Exploitation is something that, okay, so I already have a good configuration. I want to sample close by to what I have seen in the past. So basically exploiting what I know already. So the Bayesian optimization essentially sort of balances this exploration and exploitation to find promising regions in the search space, and then exploiting good regions and sample more from that region. Okay, so there are a wide range of acquisition function, and DeepHyper uses several of them. So one is upper confidence bound. You can see that any unseen hyperparameter configuration X can have mu of X, that is a prediction from the probabilistic model, and the sigma of X, that is the standard deviation from the model, right? So that is the crux of the probabilistic model. So if given an unseen hyperparameter configuration X, we can compute this, and note that parameter beta. So beta is a parameter that decides how to explore and exploit. So if you set beta to 0, it will just ignore all the uncertainty estimate from the model, and the search becomes greedy, so it performs only exploitation. If you set beta to a very large value, it will ignore the mu of X and focus only on sigma of X, which means that it will choose configurations, hyperparameter configurations that improve the validation, hyperparameter configuration that reduces the uncertainty. Okay, by setting the beta value to correct one, so usually it is set to certain values, 1.96. We can the search performs sort of trades off exploration with exploitation. So automatically decides when to explore and when to exploit. The other acquisition function also follows similar structure. You can see mu of X and sigma of X, but essentially the idea is saying explore, exploit, explore, exploit. Okay, based on the uncertainty from the model and based on the predictive value from the model. Okay, so far what you have seen is one at a time. Like Bayesian optimization is really good when you have when you want to do, okay, I generate a hyperparameter configuration, go and train a model, compute the validation accuracy, give back, and then select the next one. But it's a very slow process. Even if you are trying to do that on a reasonably sized application, if each training takes 1 hour, in 24 hours, you could afford only 24 evaluations or 24 model evaluations. And the type of hyperparameter space that we are talking about has billions of configurations, right? The space is billion, and if you afford only 24, the search is not even like looking at 0.01% of the search space, right? It's not, it hasn't seen good configurations. So the scale of the supercomputing capability is really useful here to explore the search space, right? Explore the search space in parallel. So instead of using one single GPU to do this sequentially, we can take thousands of GPUs where we can generate thousands of models and train them in parallel and take the results back to Bayesian optimization search and use that results to decide when to sample or where to sample next. Okay, so that is the key. But it is not that straightforward. We cannot just blindly sample configurations. If we have like, okay, I have 1,000 GPUs, I cannot just go and sample 1,000 configurations, hyperparameter configurations from the model and evaluate them, right? So we have to be a little bit careful here and a little clever. So that's where this Kriging believer, also called constant layer scheme, comes in, where if you want to generate K configurations, let's say you have 1,000 GPUs, and if you want to generate 1,000 configurations, the first point you select is, based on the model, you select the one that maximizes the acquisition function. Fine. To select the second point, what you do is you tell the model that your first point predicted value is right. So that's why it's called lying. And you lie to the model, its prediction is right, so that it will move away from that region. Otherwise, think about this, right? If that particular point or particular region has high uncertainty, if you select one point from that region, and if you ask another point blindly, then you will probably sample from the nearby region, right? So a point which is nearby a point which was already selected, and that is unnecessary, and that results in waste of computation time, computation resources, and so on and so forth. That's why you tell the model that your prediction is right. So immediately what happens is the model uncertainty in that region goes zero, right? Once it goes to zero, it will go and look at other promising regions where the uncertainty is let's say, not as high as the previous one, but it is still higher. If you don't lie, we would not be sampling from that region, okay? So this process is repeated k times to generate k configurations. And often the model is critical, and in a typical Bayesian optimization, one at a time, the widely used method is a Gaussian process regression. But instead of that, we use ensemble of regression trees and parallelize them, because regression trees are good for parallelization. Each tree we can build independent of the other, given the data, and because of that, let's say if you have 64 cores in a node, we can build 64 trees in parallel, and we can make this really faster. And also the parameter space is mixed integer space, right? So which means that we have to be careful how we treat the integer and categorical parameters, while the Gaussian process is really good for all real value. If you have all parameters being real, then it's really a good method. But once you have integer and categorical parameters coming in, you have to treat them carefully. Otherwise, the Gaussian process will not work. So on the other hand, these regression trees are really good at handling this mixed integer parameters. So we have two different parallelization scheme. One in which you have one manager and multiple workers. So the manager is where the search runs, and it generates different hyperparameter configurations to workers. So think of each worker as a GPU, and it generates configurations to the workers, and the workers take that configuration, run the model, and return the validation accuracy back to the manager. And all of them happens in an asynchronous way. So the challenge here is that after this works to a certain extent, but after that, this single manager becomes a bottleneck, right? So if you have thousands of workers sending data back to the manager, then the manager cannot cope up with that much data. So that's why we also designed this decentralized scheme where you don't have a single manager. Everything is distributed. Each worker runs now a search, okay? So one at a time. It performs one at a time evaluation. So it generates one configuration, evaluate it, and give it back. But the key difference is before taking that point and refitting the model, it takes data from all the other workers and then fit the model. So it's essentially a distributed version of Bayesian optimization without any single manager that is a bottleneck for scalability. The second component of DeepHyper is neural architecture search, where we are looking at how to search across different architectures, right? So this is a much difficult problem than hyperparameter search, because hyperparameter search, you can just parameterize all the hyperparameters and express this as a vector, and Bayesian optimization you can directly apply and do that. Whereas neural architecture, it's not that straightforward, right? So to that end, so the first and foremost challenge that we have is how to express the search space of neural architectures, right? And to that end, we use directed acyclic graph. An example is shown here, where we treat a neural network as a graph, and you have an input tensor that is coming in, that is the input data. If it's an image, it's an image, right? And then the first layer could be, or if it's a time series, let's say, the first layer could be different types of LSTM layers. So, it could be LSTM, here for the illustration purposes, I have all the LSTM layers, different types of LSTM layers, or it could be just identity, just copy the input to this next dense layer. Or we can have LSTM, GRU, RNN, and different types of layers. So think of the graph, each node is a decision variable, and that decision variable can assume different values. All of them discrete, no ordering, doesn't need to have any ordering at all, right? And we can think of like several such nodes where the input data flows through those nodes, and then finally we have the output. So this is how we map the search space of neural architectures as a directed acyclic graph. Now the role of the search is basically it goes to the first node and it has to select one, and goes to the second node has to select one, and goes to the third node and select one. And based on the selection, you will go and evaluate a particular neural architecture by training it and computing the validation accuracy and giving that back to the search, right? And we can also configure various types of nodes. It can be constant, variable type of nodes. For some networks, you have to fix the node. You cannot make any decision. So we call that as a constant node. But most interesting things are the variable nodes. And one thing to note here is the skip connections, right? So the residual connections, where in a typical neural network where you go from one node to the other node, right? So the data sort of flows in a sequential way. With the skip connections, you can take a node N1 and connect that to the output layer, right? Then you can also skip the N1 and take input directly and put it to N3, right? So the skip connection is essentially trying to skip some nodes, and we can make this make this type of skip connections. And the point is we can make that as a part of the search space. We are not making this connection permanent, but we want the search to decide where to put the skip connections. So why I'm stressing on skip connections is because of this. So if you take a ResNet, without skip connections, your loss surface will be like this. And the training is very, very, because of this, the training will become very hard. And training takes longer, or it becomes unstable in various places, and so on and so forth. On the other hand, if you put skip connections on the ResNet, then your training loss surface becomes really smooth. And this type of smooth surface is easy for stochastic gradient descent, where you can just start from somewhere and go to a high-performing solution or high-performing model weights in a much faster way compared to the one without skip connections. So skip connections are important to make the neural network train well, learn the data well, and it also has nice generalization properties so that it can perform well on the test data. Okay. And so we can write a search space with few lines of code within DeepHyper. And then, without training, you can just go and randomly sample how these networks look like. And here are some examples for the fully connected layer, fully connected neural network. So this is, if you work with the Keras, TensorFlow, this graph is something that you're so much used to, where each box is a layer. And these connections are basically the skip connections. These are randomly sampled, right? So we define the search space, and then now we just blindly go and randomly sample from the search space to see how these neural networks look like. And you can see the kind of sophistication that one could potentially get, right? Potentially. These are not the best architectures, but think of designing this type of architectures by hand. Impossible, right? So it's beyond human ability to even think of an architecture like this, right? And this one we can express the search space in just 10 lines, and that provides like really a flexible search space where we can go and search. Okay, so this is great. We defined the search space. We looked at how the neural networks can potentially look like, and how to search over this space, right? So that is the next challenge. And to that end, we use regularized evolutionary algorithm. So the algorithm works as follows, where you start with the randomly sampled neural networks, like what I showed previously, right? From the search space, randomly sample architectures, train all of them in parallel, and then take a subsample from the trained architectures, and then select the best one, and then mutate, right? Mutation here means, take one decision variable or one node in the graph, and then just change the value randomly. And once you change that, retrain that model, and then put that back in the population and kill the oldest one in the population. And then you do this repeatedly. So the beauty of this approach is it's computationally simple and very, very scalable, right? So each of this operation is a constant operation. It doesn't take any computationally expensive procedure. Everything is simple, and we can scale this on thousands of GPUs really fast. So with that, we looked at various types of scientific data sets. I'm going to go a little bit into the demonstration. Like, this is a NOAA, National Center for Environmental Information, the NOAA data set, where this is a sea surface temperature prediction forecast. So based on, they run really large simulations to forecast the sea surface temperatures, and the simulations take into account all the historical data, and it is a really physics heavy, solves a lot of PDEs to sort of say, what is the sea surface temperature for the next 1 week. And this has several use cases, right? So maritime and navy and ocean life, many things that are correlated to the sea surface temperature, and understanding sea surface temperature is also important for the global weather change and related phenomena. So they run really large simulations to do this forecast. Okay, so what we did is we took the data. We took a more data-centric approach. We say, okay, we took the data as a training data, and then went and ran a neural architecture search to come up with a model, right? So with a predictive model, and this is a model that DeepHyper came up with, automatically configured, right? So no human involvement except defining the search space. And here is a snapshot of sea surface temperature forecast. So this is the true forecast. This is a projected true from the simulation, and this is the predicted. So the predicted and the projected true, that's the simulation, and the one from the predictive model that is based on the LSTM is pretty close. The results are very close, and the key difference, or the key advantage, is so the key advantage here is the simulations are computationally expensive, whereas the neural networks takes fraction of seconds, and you can run it on your laptop to forecast sea surface temperature. So here is another point that I want to make with the DeepHyper. So DeepHyper is not about finding a single best model. This is about finding a large number of models, which I will explain later how we are using this capability to build ensembles. So here is on the x-axis, you can see the search time, and the y-axis you can see the number of unique architectures with R squared greater than 0.96. So this is something chosen arbitrarily, but 0.96 is a very high value for accuracy. And what you see here is the search time and different number of nodes. So here are the different workers. So for example, 512 nodes means 512 models were running at any point of time over three hours, right? So what you can see is if we take 512 nodes and run it for 3 hours, we can generate more than 3,500 neural network models that have accuracy value of R squared with more than 0.96, right? So lot of models, lot of high-performing models within 3 hours. That's a transformative capability for these type of applications, right? So we are not talking about building one model that is best for this data set, but building thousands of models within just 3 hours using 512 nodes. Okay, so here is another snapshot comparison. So this is the ground truth, HiCom, and CESM are the other simulations which takes 800 core hours a day on a Cray XC40 system to come up with this forecast, whereas the pod LSTM neural network model, it's even better than CESM, but takes a fraction of second to come up with that forecast. So the third aspect is the joint neural and hyperparameter search, where we combine both neural architecture and hyperparameter search together. So while performing neural architecture search, we can also optimize the hyperparameters of that particular architecture that is evolved. And this has several implications. And we have shown that this is a this type of methodology where we combine neural and hyperparameter search improves the model accuracy across different applications. So one is on cancer drug discovery, where we were looking at two different data sets, and one in which where we are predicting the growth percentage of the cell line, the cancer cell line so we want to see how two drugs interact with the cancer cell line, right? And the cancer cell line has a feature size of 942, and the two drugs have a feature size like descriptors size of 3,839. So the inputs is of dimension 942 plus 3,839, and there were 276 data points. So these are experiments, the data from the real cell lines. And what we want to do is to predict, given two drugs and given two molecular descriptors of two drugs and the cancer cell line, how these two drugs will interact, or how these two drugs will affect the cancer cell growth, right? And this is quite important, because you don't need to manufacture the drug to study how this will affect the cancer, right? So based on this data set, if you build a predictive model, then we can take various types of drugs, pass it through this model, and then identify promising drugs that can inhibit the growth or that can kill the cancer cells, right? So that is the key goal of this this problem. And we also looked at another problem where we have to classify the drug response for the cancer into two different classes, whether it can respond positively or negatively. So this is a binary classification problem, and this one is a regression problem. Again, we run hyperparameter search and neural architecture search for these data sets. One thing to note here is, previously I told like we use 512 nodes for training, right? So it's not always the case. For example, this one we use just 8 nodes, 8 GPUs, right? So this architecture search doesn't always need that much scale. I mean, if you have scale, that's really good, but it doesn't always need that much scale. In this case, the black line is the baseline. That's a human design baseline, right? And you can see the validation R squared going to 0.92 with the neural architecture and hyperparameter search within half an hour. So we can outperform the human developed baseline model within half an hour, right? And then the final solution quality is even better than what the human design baseline is. Even with this, right? So with the 8 node case, you can see the mixed the evolutionary plus Bayesian optimization, the mixed search produces more than 150 high-performing architectures. So we were looking at number of unique architectures with R squared value greater than 0.9. Note that the baseline is around 0.9, right? So we want to see how many architectures we can find which are better than the baseline. So the baseline is only one model, right? With the automated search, now we can find more than 150 models within 3 hours. That all of them are better than the human developed baseline. So that is the sort of the usefulness of these type of automated methods, and that's also a transformative capability for this type of applications. And here is another illustration of the models that were found by the architecture search. So look at the black one is the baseline, right? So the baseline that was that were developed by humans, and you can see there is a lot of instability in the training, right? And that is due to lack of residual connections. And thanks to the residual connections in the search, the one that is found by the automated method not only outperforms the human design baseline within 20 minutes. So this is the best architecture, best model found by DeepHyper, and we compared the training, the validation loss as a validation loss of that best model with respect to the other models. So it's quite stable compared to the baseline method, which has a number of instability during training. Similarly for the attention benchmark as well. So for the two data sets, we can outperform the best. We can outperform the baseline models. And the final part that I want to quickly touch upon is the uncertainty quantification, right? So in a lot of cases we develop models, but it is very, very important, in particular for science and engineering applications that we are dealing with, to say whether the predictions from the model is trustworthy or not. Can I trust the model or not, right? We can get the prediction, but just the prediction alone is not going to be useful. For example, take the cancer drug application, where you can give a prediction about a tumor growth, but if there is a lot of uncertainty in the prediction, you would not look at the drugs. You would not look at those drug pairs. You know, it could be for various reasons, right? On the other hand, if you let's say a drug pair is good at inhibiting the growth of the cancer cell and its uncertainty is really small, those are the drug pairs that you will be prioritizing and saying like, okay, let's look at these drugs. Let's go and do an in-depth study or do a real study on those drugs, right? So those are the implications of uncertainty with the predictive models. And uncertainty can be differentiated into two classes. Aleatoric uncertainty, which is a data uncertainty, and epistemic uncertainty, which is a model uncertainty. So in particular, epistemic uncertainty is model telling that, model giving prediction and say that, prediction and uncertainty associated with the prediction saying that I'm not certain because I haven't seen data. So all the points here are the data available for training. And if you're trying to predict somewhere here, right? So this is a ground truth. Your model should give a large uncertainty because you never had training data in that region, right? On the other hand, aleatoric uncertainty is a data uncertainty. For example, the data itself has uncertainty, noise, and you want to ensure that noise is very well captured while doing the modeling and prediction. Another example of aleatoric and epistemic is, take for example this semantic segmentation. You give an input image, you train the model. So this is the ground truth for semantic segmentation, where you segment different regions of the image, right? Based on cars, this is the payments, and buildings are in the same. So this is the ground truth, and this is a prediction, right? So this is a prediction. You train a model for semantic segmentation, and this is a prediction, right? So now you go and look at the uncertainty, right? And this is the aleatoric uncertainty. So note that the aleatoric uncertainty are all sort of far away from where we are seeing. So for example, like if the camera is here and farther away are the aleatoric uncertainty. This is because, the camera resolution is not good, which means, the data itself has noise. So there is no point in gathering more data from this location to reduce the aleatoric uncertainty. If you have to reduce aleatoric uncertainty, then you have to change the camera resolution, right? Or you have to move from this region or closer to this region to reduce this uncertainty. Whereas the epistemic uncertainty is a model uncertainty, which can be reduced by collecting more data. So this is essentially saying that, hey, I haven't seen a lot of data points that had this as a label. So give me more data points. So that's why it's important to separate aleatoric uncertainty from epistemic uncertainty. And this has a huge implication in many scientific applications. A promising approach to do uncertainty quantification is deep ensembles, where you say, okay, you have one model and you train that model with a different initialization. And then you will have, let's say 10, if you have 10 different initializations, then you have 10 different models, and then you predict from each model and then combine them to estimate the mean and the standard deviation. So despite being simple, this approach is almost the state of the art for many different applications. But the problem with the deep ensemble is that in all the prior work, the architecture remains the same. The hyperparameters remain the same, and all you change is the initialization for the training. And we find that is one of the limiting factors for deep ensembles. And what can we do? Recall that DeepHyper can generate various types of models, and those models can be then used to generate an ensemble for deep ensemble, right? So that's exactly what we did. So we ran DeepHyper, right? And then it will generate a catalog of models. let's say these catalog models are high-performing models. And from those high-performing models, we perform a model selection based on model selection heuristic and use those models for uncertainty quantification. So let's say even if you have thousands of models in the catalog, Ensemble may have, let's say, 5 or 10 that are the ensemble selection is based on the diversity and the accuracy and to avoid redundancy. Not to go too much into the theory, but essentially what we can derive is from those ensembles, ensemble predictions. We can say what is the mean, right? So mean is simply prediction from all the models and take an average. And the aleatoric uncertainty is from each model you can get a variance, and this is the mean of the variance, and the epistemic uncertainty is the variance of the mean. So it's very straightforward to derive aleatoric uncertainty and epistemic uncertainty from an ensemble of models. We compared that approach to various Bayesian neural networks, which are sort of the approach many people use to do uncertainty quantification, and compared to those approaches, this automated model generation and uncertainty quantification is more effective. Again, some demonstration here. We were looking at how to do uncertainty quantification for spatiotemporal forecasting this particular traffic, and we have diffusion convolution recurrent neural network. It's basically an encoder-decoder type neural network, which basically takes a graph, the traffic network and the state of the traffic, and then say what is the traffic, how the traffic is going to evolve for the next k time step. So basically, you give 8 to 9 as an 8 to 9 a.m. Traffic as an input, and you get the future traffic metric from 9 to 10 a.m. Right. So that's the idea. And we used this AutoDEUQ approach to estimate aleatoric and epistemic uncertainty. And essentially, what we can see is, there are certain locations which there are no significant traffic dynamics. So my aleatoric and epistemic uncertainty are smaller. Whereas there are other locations where the traffic dynamics is very high, where we can see the epistemic uncertainty and the aleatoric uncertainty being higher. So these are this type of uncertainty in the traffic forecasting helps a lot, to do proactive traffic management and rerouting and so on and so forth. So uncertainty quantification is key here.
Quick question, Prasanna, on that,
Yeah.
on that last slide. How would you get the speed? Like, because you guys work for the department, right? That has all this traffic management information. Is that correct?
So there are two ways, right? So so this is there are a lot of so there are sensors that collect the traffic data, and those sensors are sort of aggregated into a traffic management center. So either one can use that information, or one can use probe data. So probe data, the GPS data, which are from cell phones, and one can use that to estimate the speed.
See, yeah. See, I wasn't sure if you guys. So I was trying to get Department of Transportation. That was the word I was looking for. The DOT.
Yes.
I wasn't sure that you guys had access to that cell phone data.
We work with some partners who can provide that data. So this project primarily we work with the Caltrans. Caltrans database, so where they have this database of traffic over last 5 years or 10 years, and this exercise is done on that. So essentially, they you can even like pull real-time data or almost real-time data for the California network, where they have sensors in the highway, and you can pull that data.
Cool. All right.
Near real time.
Very neat.
And again, so DeepHyper is again to emphasize the fact that this is not always a software for supercomputers, but this is another demonstration where we use DeepHyper to drive experiments, computationally expensive experiments. So for example, here WASP is a DFT, density functional theory simulation code, where essentially you are looking at molecular structures, and based on the molecular structure, you estimate the energy values of that particular alloy or particular material, and so on and so forth. And DeepHyper here, the way that we use DeepHyper is in an iterative way. It's not a one-shot way, where we generate we generate, we run multiple simulations, right? And take the data and run the DeepHyper and generate ensemble, and then from that ensemble estimate uncertainty, and based on the uncertainty select the next set of simulations to run. And those simulations will run on hundreds of nodes, but then it gives the results back to DeepHyper, which runs on a single node. Again, once you get the results, you run the DeepHyper again, and generate an ensemble and use that uncertainty to decide the next set of simulations to run. So the simulations take several hours to run, whereas the DeepHyper for the ensemble generation here takes few minutes to generate ensembles. So this is another demonstration where it's not always about scale. We can run it on a single node, generate ensembles within few minutes, and use those ensembles, use uncertainty quantification from the ensembles to drive computationally expensive simulations and experiments. So this is to say, like, we have users who are using it on a single node on a laptop. If the data set is not large, you can just run it on the laptop, run it before you go to sleep, and the next morning, probably, depending on the data set, depending on how many models you evaluate, you can get the results the next morning, right? So you are not sitting there and doing all the trial and error process. On the other hand, if you have like a cluster or a cloud or even a supercomputer, you can scale this. So that's the key advantage of DeepHyper. It can run on a laptop and all the way up to the supercomputers. So we can configure in various ways.
Yeah, that was one of the quick questions, I guess, that Matt had dropped in here. Do you have to modify anything really to make models or applications developed on your laptop run on the exascale computer? Is it kind of really much exactly the same? Is there really any change that you have to do?
There is a change, but the change is primarily on the supercomputer side. So the supercomputers have this type of queuing system and how to run the jobs and so on and so forth. That changes from one system to another system. Some of them use Slurm, some of them use Cobalt, and so on and so forth. So we have to deal with that change. But on the laptop, it just works out of the box, no problem. Similarly, we also use Ray as a workflow manager. So Ray sort of works in many different settings. It works on the laptop. So for example, Ray is a sort of a workflow system where we say, okay, a manager and a number of workers. So you can configure a number of workers on your laptop, let's say 5 workers or 10 workers, and say, okay, Ray runs it, right? So as long as the Ray is part of the install as well, so it is seamless. You can run it, you can install it. So the Ray workflow system take care of that aspect. So the primary change comes from whether we use Ray or we use some other workflow manager. And in the supercomputers in particular, we have to do some configuration. And often, this is for different systems, we already do that. But if you're looking at sort of a cloud, or if you're looking at a laptop, this should be straightforward.
Great, cool, thanks.
And here are some links on the tutorials. In fact, we have a Google Colab. So this is not listed here. This is a little bit older. So now in the tutorial section, we even have a Google Colab notebook where you don't have to install anything. You can just try out some of those examples, like hyperparameter search, neural architecture search, and so on and so forth on the Google Colab just by running them. So please do check that out. Credit to my co-lead, Romain Ijalet, he did a lot of work and an instrumental developer in the project. And it's again, it's not just me and Romain, it's a community effort. And here are some people that I could put within the slide. There are many others which I cannot put them in the slide, but a lot of credits to these people. Some references, the algorithms that I talked about, scalability I talked about, these are all published in some of the top conferences. That includes supercomputing conferences and you can definitely check out these papers for more details. Acknowledgements to Department of Energy, Department of Energy's, in particular Department of Energy's Early Career Research Program that funds this project, DeepHyper project, and also Argonne Leadership Computing Facility for providing the resources to run experiments at scale, and also labs internal funding. Yeah, so with that, I conclude my talk. Here is the link, and please do check out, and I'm happy to answer questions that you may have.
All right. That's awesome, Prasanna. Wow, you got into a lot of stuff here. I mean, I guess I'll open it up to anybody if they would like to unmute and ask any questions. I certainly have a couple here on my side too. I know we're running a little bit short on time, but we can spend at least 10 minutes here going through any questions. If anybody wanted to either type one in or feel free to unmute here real quick.
I had a question.
Yeah, go for it, Carl.
What I'm wondering is, one of the problems you have is having enough training data to do all the things you want to do.
Mm-hmm.
Is there a way to use knowledge you already have to affect the neural net such that you don't have to have additional training to get the system, get the neural net to come up with the same knowledge you already have?
Fantastic question. So we call this as a physics-informed neural networks, where we incorporate a lot of physics into the neural networks, either in the architecture or in the loss function, and that is definitely possible. The loss function is independent of the architecture search, but here is the catch. So as soon as you start adding those physics knowledge as a constraints in the loss function, your loss surface becomes rugged, right? So loss surface becomes difficult. And given that you don't have a lot of data to train, if you don't add skip connections, then that becomes a problem. So that's why the idea of using skip connections for physics-informed neural networks is a very promising approach, and that's something that we use a lot. So clearly, yes, we can incorporate the physics knowledge or the domain knowledge into the architecture and in the loss functions. So in terms of architecture, think of these molecular features that I talked about. So where that aspect, like two molecular structures or two molecular descriptors on the cell line, the way that we construct that neural network is these molecular structures, they will have some layers, and then they will be connected. And the cell line layers, they will have a certain number of layers, and they will be connected at the end. So we don't mix all of them at the same time. This is because we know that the molecular structures, we have to combine them because they interact, right? So we have to find representations for that. And the cell line should be independent of that, right? So this type of domain knowledge, we can incorporate that in the way that we define the search space. And the other knowledge is about the domain can be incorporated as a loss function, as a constraints in the loss function, and so on and so forth. Yes, you are absolutely right. Incorporating this domain constraint significantly reduces the need for data, and that is possible. And the difficulties posed by such incorporation can also be addressed by using architecture search.
Yeah, you were talking about each different, essentially incorporating different type of machine learning models, I guess, right? Like LSTM and some of the other ones. And of course, from what I understand, it kind of rolls through one version. It does some of the skip stuff, and then maybe it tries a different machine learning model. Are there ways to essentially, at each neuron, kind of try a different activation function? And it just kind of occurred to me if that's even possible.
As long as, so the activation, so whatever that can be supported by the underlying framework. So, what we have is, what we built is on top of TensorFlow and PyTorch, right? If the TensorFlow and PyTorch allows such things, then we can definitely do that. So right now we have this layer-wise activation function, right? And the granularity that you are asking, I think I need to check if it's possible within the TensorFlow and PyTorch. If it is possible, then we can definitely do that.
I see.
So
Okay.
think of DeepHyper as a sort of a wrapper on sitting on top of TensorFlow layers and PyTorch layers, and all it is doing is manipulating those layers. Sort of taking those layers as a building blocks, and then putting them together.
Gotcha. Yeah, that was sort of a follow-up question is, yeah, did you guys write all this stuff internally? But it's like, no, you guys are just playing with a lot of the weights and just, I mean, there's just infinite number of different combinations when you run these models. So you guys are really hyper tuning those, right?
Yeah.
This is a more high level question. I mean, how have you seen supercomputers change, I guess, over the time that you've been there? You mentioned, I think 64 GPUs at one point. To me, that sounds like insanely powerful. And that you could pretty much do anything, on that. Obviously, you guys are dealing with a lot of data and you guys have to churn a lot of things, but just on a standard level, like where are things headed and kind of where have they been while you're there? Have you seen dramatic changes?
Okay, so the previous generations of supercomputers, they were primarily architected for simulations, like numerical simulations, right? Trying to solve PDEs and so on and so forth. The new generation, it's a simulation plus learning. So these systems are architected not only just for simulation, but also for machine learning. Oh. And in particular, we are talking about machine learning, we cannot ignore GPUs, right? That's the sort of the current, like the exascale systems that are built are primarily based on GPUs. They are not NVIDIA GPUs, but they are GPUs from AMD and GPUs from Intel. These are new set of GPUs that are coming out from these vendors, and those GPUs are architected for the type of applications that we have. Okay, so we have if we have to do data parallel training, model parallel training, or if we have to move data from simulation to learning, right? To the learning node, then we need a very fast interconnect that sort of connects not only the GPUs but GPUs across nodes and so on and so forth. So that's a sort of new things that are happening in the current generation, right? And also the storage system and the memory, these are all evolving according to that. Like we are talking about storing large amount of data within a node. And to perform really large scale training, right? So within a node now we are talking about multiple GPUs, and can we do data parallel training? Can we do model parallel training? And each data point could be a tensor, and that at a given point of time you cannot handle thousands of those points. So we need to sort of stage the data and so on and so forth. So those are all the interesting things that are happening in the current generation, but also the next generation of supercomputing is moving towards some interesting architectures. For example, we are working with several startups, Cerebras being one, where we have a wafer scale chip, right? So it's a huge chip where you have a lot of compute. Similarly, Samanova. Samanova and Habana chips and so on and so forth. There are new set of AI accelerator chips that are coming, and the next generation is going to be even more interesting. It will be a mix of these different architectures. It will be GPU, Cerebras, Samanova, and others, right? So it's sort of a mix of different types of chips that were sitting in a single node, or in a single rack. You will have different set of nodes with different different accelerators, and that makes the problem challenging, but also there are a lot of interesting simulation and learning one can potentially do.
I think Matthew had another question.
Yeah, I was actually just typing it right now. So you mentioned that DeepHyper can work with either TensorFlow or PyTorch models. I was just poking on the documentation on DeepHyper Ensemble because that sounds like really exciting and promising. I'm noticing that it only works with TensorFlow Keras models, the H5 format. And is that accurate, or is that something like future development you want to work with both TensorFlow and PyTorch there? Or
yeah, so you are right. So right now the version on the main branch supports only Keras and TensorFlow. There is a develop branch which is sort of work in progress to bring PyTorch into the mix. In fact, we are working on a wrapper where we are trying to encapsulate or trying to sort of abstract both TensorFlow and PyTorch and have one wrapper that can handle both of that. So that's a work in progress, and it is happening as we speak. And hopefully, like in a couple of weeks, we will be able to have the support for PyTorch.
Awesome. Yeah, I suppose watch the library to find out when it comes out.
Yeah, absolutely. Please do reach out. We are happy to help you to get started with the PyTorch, because you are not the first one to ask for the PyTorch support. that's the reason. Like we try to have we are trying to have both. Having said that, we can support, if you are doing only hyperparameter search, then PyTorch or TensorFlow doesn't matter. For the neural architecture search, currently we support only the Keras layers, because we are manipulating the layers, right? So we are calling the layers in the search, and right now we cannot, we don't have an interface to call the PyTorch layers yet. So if you are doing hyperparameter search for PyTorch, you can do it now. Then that's not a problem. But if you are doing neural architecture search, only Keras and Keras layers are supported, not the PyTorch layers.
Very cool. Just a quick comment, the whole thing about doing a distributed worker, I just took a quick note on that. That is very, very cool. Not having this one sort of master trying to delegate all these things. That seems very, 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 very efficient. That's a brilliant move for you guys to build that.
Yeah, actually, we, it's something that we encountered. So we have a new machine called Polaris. It's an NVIDIA GPU machine where we are trying to scale this up, and we are getting ready for Aurora. That's our exascale machine, where I showed a little bit of preview on that. If we have to run this over 10,000 nodes, where each node has, let's say, 4 GPUs, we are talking about 40,000 workers, right? And none of the existing Bayesian optimization method can scale. There is no technology available, and that's where we say, okay, if we have to do this at scale, because scale is like very interesting and important, right? So as I showed, within an hour, imagine when we have an exascale machine. When we have an exascale machine, we can generate thousands of high-performing models within an hour, right? For wide range of applications, and that's a transformative capability that we are after, and that sort of opens up so many new possibilities for scientific discovery. So essentially, we have to solve that problem to run on big machines.
Sure, understood. Well, yeah, it's a great solution for sure. Well, great. Prasanna, I appreciate you taking the time here tonight, going in depth all about DeepHyper, sharing your experience and everything with the project. And I posted a link here in the chat with regards to sort of a direct link to our podcast, encouraging people to share that out on their network. And I know you'll be sharing that within Argonne as well. So you and I had a chance to talk in depth about this project and about your background and about everything you sort of do at the lab, which just sounds very, very fascinating. And I know you guys are hiring in a bunch of different areas. So it sounds like a really cool place to work. So put the pitch out for there as well. And again, I appreciate your time. Thank you for sharing all this information.
Thanks, Justin. It was great.
All right, I'll stop there.